So let's see. So anyway, the homework, like some groups did really well, and other groups did really poorly. So it was kind of a mixed bag of stuff. So I guess I should go through this thing, but anyway, it seemed like what they did poorly on were the things that should have been just copy from the notes, like the equation using obtain this using the Legendre. So uh that's similar single component. So that basically was that question is just asking you to do this thing. It was already, let's just go through this and get that expression. People, some of the answers were like 5 pages of derivation. That was kind of crazy and stuff that didn't make any sense. So, I mean, I guess if you run into trouble with this stuff, just email me and I'll try to get back to you right away. I sent out an email that said something like, go to the notes. Was it for this question or? Oh, okay. Well, I guess it didn't. Oh, wasn't? Okay. All right. So you just gotta like email me, like, and let me know what's going on. If the ship is sinking, I'll send you some kind of life preserver. I'll just tell you what the answer is, in fact. So just it shouldn't be that you lose points on these kind of things. Anyway, it happened. So there was that thing. So anyway, it's just like doing the derivative and then doing the second derivative and then equating the two terms. It's the same as this thing. And then do that with the A prime instead of A. I don't know if that helps, but if you still have a problem with that, email me and we can, or if you want to ask now, but anyway, so there's that one. Then so that alone, like that expression alone doesn't indicate a second order transition. And that's just like that's a general thermodynamic relationship. Like the Maxwell relationships are just relationships. It doesn't say anything about order of transition. So a couple of these were kind of leading the questions, kind of leading you in the wrong direction and kind of asking you to pull it back. So anyway, that doesn't indicate it's a second order transition. That's just a Maxwell relationship, right? So the second order is, he goes through and he shows that this is a continuous transition, and then Loss shows this business about first order, second order. So he's got can you see? Is that okay? Anyway, so this view is first. He shows the orange one, I guess, yeah. And then also the business of this plot, like if this is a positive slope in this, then it's second order, and if it's a negative slope, it's first order. And this what is it called? R something plot, right? R plot. Right? So anyway, that's kind of his definitive proof that it's second order. That and the thing that shows that it's second order here. So it isn't, the Maxwell doesn't tell you that. I mean, so one answer to this is it doesn't. It doesn't indicate that it's, that's just the Maxwell equation. Anyway, or you could, I think most people that got it right went in and said like, because it's continuous, like whatever I just said, something along those lines. And equation 2 is the thing, is also from the notes. That's just that's like the first few slides in this solution stuff, which we did kind of Thursday, but basically ABC, just go through these like we do this thing. It's like you can say, you can do this from a pressure point of view, and then use ideal gas for P for V, then get dP as you want, P over P, and then figure out P over P. If you use Raoult's law as X. And the other ways of volume method, similar to that. It's a little bit more involved for the volume things, but kind of the same thing. You end up using ideal gas law to replace somewhere dV. So P replaces 1 over V, so dV over V gives 1 over V. Then it's V final over V initial. And final is a total volume, initial is a component volume going into a mixture. So the negative of that is a volume fraction, which if it's an ideal gas, the same as a mole fraction, yes. If it's incompressible, it's ideal, another word for ideal mixing. So all these involve, all this, and this term is always going to involve some kind of ideal, right? So it means no enthalpy. So this is just an entropic term. And then the last way kind of directly says it's just entropic, because you use Boltzmann's law to get to calculate the same thing. And that's just a calculation of the entropy. So that means that there's no enthalpy, so it's still ideal. So the three methods, kind of three different angles to get the same equation. And they all are based on some kind of ideal, like no enthalpy of mixing. So anyway, that's a fundamental thing. So if you see in a paper they have x ln x plus x ln whatever, then you know that that's some kind of ideal mixing rule. And then there's going to be another term that's added that will take care of this enthalpy of mixing, this delta H. Right, so you'll see that, I mean, you'll see that over and over and over again, like this kind of XA ln XA, XB ln XB. So you have to kind of accept that as that's kind of a safe point for we should be able to say like you're comfortable with what's going on with it. So A and B, like those are the two things people lost a lot of points on. So I thought those were, anyway, basically it was just the notes. It should have just been go to the notes and kind of regurgitate it. Basically, there wasn't, except for this thing about does this indicate second order. Any questions on those, comments or anything? Yeah, right. So then the arrow plots. So there's a couple twists to this thing. So one thing is, let's see, so there's a wiki page here that you have to go to that it gives you. I guess. So, this thing. I see this actually goes through the whole thing, like I think. Let's see. Well, it gives, this is the Landau theory. So it asks you like, how does this relate to Landau theory? This is the answer to that. And then this is just rearranged to get this equation. This eta is T minus TC over TC. So at the critical point, this thing goes to 0, that term drops out. And then m squared, so this is a plot of m squared versus 1 over h over m, right? So that would be a straight line if this term doesn't exist. And then if you're below TC, right, then you're in the ferromagnetic regime. And this term's negative, so you get like a negative deviation, I guess. And then when it's above TC, you're in paramagnetic, and then this thing adds a positive term. So then that leads to like a positive deviation. So you should have a straight line, positive, negative. The other thing is that this thing, so when the magnetization goes to 0 at the magnetization should go to 0 at the Curie temperature. So this should go to 0. Like it should be a straight line, it should go to 0. Right. So that's kind of the theme of this. Like this plot should give you a straight line goes to 0 if you're at TC. And if not, you get these kind of curved things that don't go to 0 at the intercept. Like y and x are both 0 because m. All right, so So then, all right, so they aren't though, so that's because you have this kind of critical exponents, which you'll hear about, which means critical fudge factor. So they say critical exponent means they don't really know what's going on. Right, so they're going to just take that same equation, raise it to some power, and then they can get the thing to straighten out into a straight line. Right, so they'll talk about critical exponents. It should be one if it follows the law, follows this Landau theory. If it's not one, it means something else is going on. They can't really explain, so they just stuff in a number to account for it. That said, like that exponent, like people do their whole PhD in physics or something on that exponent, like criticality is like an area that's studied in physics, and this critical exponent is like the main subject of it. So what value that fudge factor has kind of matters. And then you can have a brittle transition or like call it brittle or soft or something. So you have different, depending on the power of this, you can describe like what kind of a transition you're going through. So that's why they mentioned this critical exponent business here. We'll talk more about that later on, I guess. Or if we pick up a paper on class transition, that exponent becomes like the main, like one of the main things people look at. So that's just like piddling around this thing, and it's got something to do with Landau, critical point. So it's just to get you familiar with a few things. I don't think anybody lost big points on this thing. And then this business, like people, so he says in the paper, and I think I pointed out in an email that the guy gives this thing like this RC or this RCP, whatever he calls it. That's the amount of ice you can melt, basically. So it's like delta T, delta S max. That's the figure of merit for this thing. But that's how much oomph you can get out of this magnetic transition. So that's basically find the T range here, find the maximum, multiply those two. That'll give you units of, I guess, joule per kilogram of stuff, of the magnetic material. So say you have 1 kilogram, then compare that number of joules for 1 kilogram of your magnetic material with ice. You find out that it's like nothing. I think everyone got nothing for it, but they got to it from different routes that weren't right. Basically, some people got really small numbers, but it's like a fraction of a gram, like half a gram. So for a kilogram of this stuff. So if somebody went in and figured out for their refrigerator how much of this material they'd need, and they ended up with like 1,000 kilograms of some huge amount, it's basically your house would break. I mean, it would be enough to destroy your floor. So it definitely would not go on a spaceship or anything. Right. So it kind of shows you like, so why are they doing this? It's kind of a question you should ask yourself. Like, right, it isn't a very highly cited paper, this particular one. And also when you look at the law thing, she gives that kind of weird circle thing, and the magnetic thing is a small chunk of the pie here. And the reason is it doesn't do anything, right? I guess it's not really a functional material. So anyway, still kind of interesting, but it's not going to change the world. I'm not going to use it as a refrigerator, I don't think, at least from what they show here. In this business, so he calls it high entropy alloys, and then because it's 5 components and there's entropy involved in mixing, and that has basically nothing to do with the magnetic transition. But even though the magnetic transition has to do with entropy. Oh, okay. Actually, I don't think I brought the sheet of things I wanted to talk about, but one thing just I remembered. But so people kept saying, so they answered this by saying this is so efficient, like a refrigerator is efficient, right? So you have to, with refrigerators, you have to do this thing called coefficient of performance. Pop, yes, maybe not that cup. Coefficients of performance, right? So it's basically the cooling you get out over the work that you put in. right? So there's no efficiency for a refrigerator because of the way this works. So if you have a Carnot refrigerator, it's like you can calculate this from the temperatures, like the hot, cold temperatures and hot temperature. And that would be the maximum. The Carnot would be an ideal refrigerator, and that would be the maximum. This number is going to be like bigger than one. It's not going to be, efficiency would be like up to one and then below, and this is going to be bigger than one. And it tells you just how much oomph you're going to get for the work that you put in. And this would be like the best that you could possibly do, like the hot temperature over the difference in temperatures that you're trying to get. So the bigger the difference you try to get, the smaller the coefficient of performance. Right? And then these would have to all be in Kelvin. You can't use centigrade here. Right, so there you can see this number could become a pretty large number for an ideal system. Like if this is 300, you're trying to cool it by, I don't know, 25, and it ends up being 12 at the value of 12 for the coefficient of performance. Ideally, and a typical refrigerator is going to be 2, like the one in your house. If you figure out one of the groups figure out the coefficient of performance for this refrigerator, because you have the energy, the cooling energy, and you have the work you put in. Basically, it's between 1 and 2. So it's something, the coefficient of, if you want to call it, it's not called efficiency, it's called coefficient of performance. And it's kind of worse than the refrigerator in the kitchen, but not that much worse, like half as good. Right? So anyway, if you took thermo, like depending on which branch you took, like if you took it in physics or chemistry, you would never hear of this. Right? But if you took it in mechanical, this should be something that you heard of, because mechanicals end up working in refrigeration. And chemicals, this is part of their class too. If you studied the Carnot cycle, Carnot engine, you must have done coefficient of performance, because there's 2 ways to do it. It's like a heat pump thing. It's either have cooling or heating. So it's either an engine or anyway, so that's the deal. Like talking about efficiency in this answer, like what's the advantage? First off, it doesn't have an advantage of efficiency, I mean, of coefficient of performance. And second off, efficiency is like a no-no word with refrigerators. If you don't, unless you want to say like, how is the coefficient of performance compared to the Carnot coefficient of performance, like the ratio of the 2, like say you got 2 and it was 12, then you have 1/6 or whatever of the Carnot, of the ideal. Then you could say that would be, and if you had it 100, you'd be at the Carnot, that's as much as you could get. That's the best it could perform. So whatever, but basically efficiency is a red flag that shows up here. If you start talking about refrigerators and efficiency, it's just like, that's like some kind of gears are grinding there. Something's wrong with it, right? So anyway, that's it. Any question? Again, like I think 3 groups did like great, and then like some groups did middling, and then a couple, 3 groups did terrible on this one for whatever reason, If you're doing terrible, if the ship is sinking, then email me as fast, even if it's like 2 minutes before it's due, or if you're requesting an extension or whatever, I'm trying to get you to get an A, so I'm on your side. Don't think it's like you can't contact me about it, because I get 2 emails. That was it, and I should have gotten probably like 5, right? 5 or 6, because from the results of the looking at what happened. So anyway, did you have some question or anything?
Yeah, part C, those figures, seems like the straightest line going to plot, given the way near the origin.
Yeah, you mean, and I noticed that too. So I think that's got to, all right, I don't have any idea, but basically I think that like over here, those are the ones that look like they're, yeah, I thought the same thing. So I thought that was the transition, but apparently it's like over here. And the reason it isn't is because of this thing. I mean, I'm hand waving here, but it's because of this gamma. Like in other words, if you found the right gamma for that system, then they go straight lines. Then you'd plot, instead of 1 over m, you plot 1 over n to the, or h over m to the 1 over gamma, and then you'd basically get that to be a straight line by sticking a power in there. It's cheating. But then the gamma has some information. What information it is, it's hard to tell. I mean, basically can talk about the rigidity of the transition, I guess they call it. So if you have a rapid kind of glass, or if it isn't magnetic, if it's a glass formation, then you have like a rapid glass formation versus a slow glass formation. So that gamma would tell you what kind you have, like whether it's so. And in terms of magnetic, it's probably the same thing, like how fast does it? So it's going to be like all the directors are flopping all over and they're going to go to something, right? Go to ferromagnetic. So does that happen like in a kind of a gradual thing, or is it like a quick transition, you know? So the gamma, I guess, can reflect that depending on the value of the gamma. And that tells you if it's a glassy material, it tells you something about the kind of the disorganization of the material and how easily it is to lock in, like something like some kind of metaphysical thing that doesn't mean much. I think it's not, this gets into, again, like people write long books about this scaling coefficient. It's a popular topic among people that are kind of wasting time, I think, because I'm not sure what the relevance of it is that much. You know, it's mostly just to describe these kind of second order transitions. And the fact that you have a model and it, like you said, it doesn't go through zero. So what's with that? So you can explain it with that. That's why they stuff that in here in the wiki page. It's a good question.
Saw the high end of the spread was 108, but warranted the extra credit. Can you go through the response that was? Is that what
they were like smoking through the thing, like it was really well done. I don't remember the details. I'd have to bring it up. I'm not sure if I should do that. It's in what kind of it's gonna give me Canopy.
it's Kansas?
Yeah, but I get to Canvas through Canopy.
Okay.
Canvas. I don't know if those guys. You shot.
I had to if you go back, for some reason that link underneath the main link doesn't allow you to log in. But if you go to UC's page and then click on the Canvas link from there. I'll just tack on the Canvas at the end of this.
Oh, wait, did I miss it? This Canvas here. Anyway, why don't I not do it now? I don't know. I don't really want to go through their homework unless they say it's okay.
Yeah, that's great.
So why don't I skip that for now? All right, so it was just like they were just, I mean, you would see exactly what I mean, like they were just smoking through it, like it was just something way beyond what was asked for. And everything was perfect. And I don't remember, it's something that you look at and you're like, wow, that's pretty good. Let's give them like a couple points. It's kind of hard, it can be different things.
Yeah.
It can just be like, you spent a lot of time and you found something interesting and you put that in there or something, or it could be different things. It doesn't have to be whatever they did. But they were just mathematically, like the thing was really squared up, you know, that's what happened there. That's where I remember it anyway. All right, any other stuff or things? You can probably figure out who it was, right? What group, I mean,
Question.
yes.
I've been considering, for the home where it was, they were kind of challenging. I think what would make it a little easier, at least afterwards for the explanation, if we had a right answer, like a paper with, you know, this is how it should be written and done.
Uh-huh.
If I,
Yeah. I don't know, there isn't exactly a right way, though, so.
well, I
everyone's
mean, like, you
answer-
know, if you just said, this thing or whatever, like you have a question, A1, and then asks for Maxwell's, how to differentiate into the exact equation. Exactly like, you know, the answer that you would have said, this would be a little bit more acceptable if you said this, and you put that particular answer, so that way we can have a little bit, you know, guidance. I'm doing in the future.
Yeah, I think that there's more than one answer. There isn't one answer. Anyway, the first two are just copy the notes, right? They're directly from the notes, from the PowerPoint. And then this I kind of just went through, right? The error, and I'm not sure which one did you guys lose points on. Is it one CDE that are the points, where the points were lost there? All right. Okay, is there any other stuff? I mean, I don't really want to do that, I guess, is what it comes down to, because I think there isn't one answer. There's no one answer to it. You could give two answers, they could be completely different.
Yeah.
Like they could come to different conclusions, and
Yeah.
both of them could be right.
Oh, no, I definitely understand that. I was just saying so far as, even if there's like more than one answer, a particular answer of like what could have said, or, just come loosely.
I mean, you have to find your own voice too. It doesn't have to be like my voice of what things are, but it can be your voice. It can be in your words, like how you say things, It's the point is to see how your brain works. To fix the parts that aren't working the way they should be, to leave the parts that are different,
Yeah.
Because without the different, no advancement is going to be made. Right? If everything is the same and it's copied from something that I say, that's not good. That's a bad thing, Good thing is you say something, I don't agree with it. No, that would be the best thing when you're right, That's the best situation. I don't know. I think it's better to leave it open. And you're working in groups, right? And you're mixing with every other person in the class. You can see, hopefully, what the spread is. But keeping your own voice is really important. Don't let it be that you have to be within a certain framework, Otherwise, there's no progress. Like nothing can progress. Right? Oh, this guy. All right, yeah, there is one other thing that reminded me about progress. Okay, so I asked about like this equation, right? I don't think I think one group maybe picked up on this. So this equation's all screwed up, right? I mean, this is totally messed up. Like, this is a subscript. The M is subscript. It's not, that M is subscript. Subscript, this H is subscript. People were arguing like why you would have H here. Like someone went through quite a bit to say like why you would have H. It's like just screwed up, Like if you got the Maxwell relationship, you could clearly see that there's no SM, like that doesn't exist. That's not part of it, So anyway, so here, this also should be subscript. See, it's just like they didn't proofread the paper. It's pretty weird. Like, all right, you would think either the referees, the three people had to read this paper. It's a pretty good journal. I think Materials Today, Physics, isn't that an MRS journal or something?
The editor does not care about.
I mean, what is this? Like, what is this? It's a main equation of the paper, right? That is the main thing. It's like totally messed up. And like the authors didn't read it. And then the three reviewers didn't read it. And the editor of the journal didn't read it.
All reader does not care.
I mean, goes to show you that, I mean, you have to like, I apologize that I didn't I didn't realize that until I started grading the things, and it's like, what is this thing? The other paper is a little bit different, right? It's like, she's got this conversion factor, this mu, which I guess is like susceptibility or something. I don't know what mu is. She doesn't define it. But basically, you can accept that because it's just some constant to convert the units, kind of more or less. Right? So, but here, this thing's totally messed up. Like unless you know that the C delta S is sub M, and then it's like SM, totally messed up, right? And this should have been sub H over here if you followed the Maxwell equation. So I don't know what to tell you. It's kind of like, I guess you have to be able to pick that up, but I glanced at it, I didn't notice it. And then I went to look at it after I'm grading them and I said like, wow, that's pretty messed up. And then some of you guys like spent some time going through it. So anyway, there's probably a few other things. I didn't bring the sheet, but I took notes on when I was grading these. So any other things on this? So it was like people, like some people did really well and then others didn't. So I think that if it looks like it's going bad and you don't have any idea, you have to email me. Just keep hounding me about it. And I'd help you do it now. Then that's about it. I think that's everything here. Yeah, you can remember this. Grams of ice. People tend to not sure if this class or the other class, but people, it's the other class more than in here, but people tend to hedge their bets. Like if you say, comment on the usefulness. If you think it's great, say it's great, that's good. And if you think it's lousy, say it's lousy and don't hedge your bets by it's good, you know. I guess maybe this question isn't good for that because this is good and bad because the mechanical properties are good. Anyway, I guess it's the other class. I shouldn't mention that here, but basically hedging your bets is not a good way to go about things. I think it's better to pick a side and argue it. And then if the other reverse argument is convincing, then accept that, you know, if you can. Otherwise, keep fighting. You know, so anyway, so is that business. I'm not really coherent today. I had this flu shot yesterday and I'm kind of like, I don't know, not in great shape on the solutions. It was like a quadruple flu shot. I thought that sounds like a good idea at the time, but in retrospect, I wouldn't have done it. So anyway, so there's a few things to go through here. This is the wrong guide. This is the other guy. Solutions, right? So we kind of went through that. So we have this delta S, we have that delta G, but the real delta G has a delta H in it. Right, so we have whatever my thing is. Here I have here. So delta G's S delta T. Let's see. So G is H minus TS. Right, so we have that from the square. And then so we need an H on this thing. This is just a delta S. Right. So G, if it's ideal, G is minus T delta S. That's entropic mixing. Then you need to have this somehow add in this enthalpy term. Right. So how do you do that? Well, the way you do that is you say if it's a binary mixture, which is usually like 9 out of 10 times it's two components, like A, B. So then you say there's just going to be a binary mixing, like you have x1, x2 times some constant. And the constant. So if you pull the temperature, the RT or KT, depending on molar or a number, right? Then you take the free energy divided by KT, then you have this, so this term, the entropic term, which normally is a temperature dependent term. So if you plot like free energy versus temperature, the thing that changes with temperature is the entropy. The thing that stays the same is the enthalpy. But if you divide the free energy by temperature, which is the normal way to do this, then you end up with this term as temperature dependent. So you have this fixed entropy of mixing that normally is temperature dependent. This not temperature dependent because you pulled out the T. Then you have this A12, which is temperature dependent because it wasn't temperature dependent. Now it is because you divided by T. So this should have a 1/T dependence. So let's call it an interaction parameter. So Hildebrandt kind of invented this thing. I'm not sure when. Hildebrandt was a Dutch guy, and then Margulis, I think, was an American. So Margulis was like a chemical engineer, and Hildebrandt, I think, was a chemist. That's more or less how this worked. But it's the same approach, though. It's just binary interactions. So if you want to know how many 1-2 interactions do I have, it's going to be proportional to the probability of finding a 1 times the probability of finding a 2. That's how many 1-2 interactions I should have if the world's fair. Right, so this can be omega for the Hildebrandt. It can be A for the Margulis 1 parameter. And then that can be the chi parameter for polymers. So polymers have a couple problems. For one thing, so these X's in a polymer are going to be per mer unit, and they're chain molecules. They're glued together. So if you have 100,000 units in it, there's 100,000 little things. They're glued together in a chain. And they have the solvent, which is kind of like one thing, right? So they're different sizes. If you mix it, the chain kind of moves as a group, right? So it's only going to be like one of those. You have to take this X and divide it by N in order to account for the fact that the polymer is glued together. So it doesn't get the entropy that it would have wanted. You have to divide by N. The other thing is that the volume of one of those mer units isn't the same as the volume of one of the solvents. So you use volume fractions instead of mole fractions. You end up with this equation that looks a lot like this Hildebrandt equation, except instead of A12, you call it chi, which is like an X, it's like a squiggly X in Greek. And then, so it's called the chi, Flory-Huggins chi parameter, or the Flory-chi parameter. And then instead of X, you have volume fractions, and then you divide by the molecular weight of the two components as the prefactors here. So you end up with this business. Right. This guy has that equation here. So when you see something like this and you haven't seen it before, so you say, oh, X1, ln X1, and I'm happy with that. That's my entropy. Like you can see where the entropy is here. But then you say, oh, that's not X, that's some weird Greek symbol. So, and you look and he says that's volume fraction. Right? So he's got volume fraction, and then he's got these N's, which are the molecular weight of the two. He's got two polymers, quote unquote, polymers mixing. So his polymers, right, so it's a simulation. So his polymer isn't 100,000 like a commercial polymer. N here is 4. So these are what you call oligomers, right? He even calls it oligomers here. They aren't really polymers, but he says they look kind of like polymers, so I can call it polymers. They're really just organic molecules, right? But so 4 isn't really enough to. So anyway, so he's mixing these two things that would normally not mix if they were really like polyethylene and polyethylene oxide, or what's the other name for that? This PEG, PEG, PEO or PEG are the same thing. Right, they don't mix because one's polar, one has oxygen, the other one's like an oil. It's just carbons. So they don't mix. But if you make them just 4 units long, they do mix. It's like that's the reason why it's going to 4 units. One of the reasons. The other is if you're doing a simulation, it's much easier to have these short things. I mean, it's going to be much faster instead of a long computer simulation. So anyway, so yeah, this equation has a couple twists to it, but basically the same thing, right? Here's your X1, X2, which are phi1, phi2, and then times this chi parameter, and this is 1/T. We expect this thing to have a 1/T dependence, right? And it's gonna be the average interaction energy between the two things divided by KT, because you divided by KT over here to make this thing not temperature dependent. Right, so you're gonna kind of look at the temperature dependence of this chi, and it should be a straight line in T. It should just increase with temperature. a decrease with temperature. I mean, versus 1/T with decrease in temperature. He probably shows that in here somewhere. These are the gammas. No. All right, so he doesn't do that. We'll talk about that later. All right, so this is along the same track. Like we have this A12. So this is going to be the average energy of a 1,2. So energy of interaction between 1 and 2, and then minus the energy of interaction between 1 and 1, minus plus the interaction of 2 and 2. So it's a difference in energy between. So if you have a 1,2 interaction, that replaces a 1,1 and a 2,2, but it's going to be like half of that. So it's 1,1 energy plus 2,2 energy divided by 2, then subtract that from the 1,2 energy. It gives you the average energy change for a 1,2 pair in the thing. And the probability of finding that is going to be x1, x2, whatever that is. x1, x2. So this is kind of like just straight brute force, kind of just write an equation. Turns out that equation works great. One problem with it is it's symmetric. It's totally symmetric about composition. So the critical point for it is going to be at x1 is 0.5, and that isn't always true. Because if you have something like water mixed with alcohol, like the water has a strong association, so it's going to shift that curve over. Right. And also if you have a molecular weight dependence, it'll shift the curve. Like if one's large molecular weight, one's short, it'll shift the curve over to one side because the high molecular weight things are less miscible than the low molecular weight. So it'll shift this curve. But from this equation, you can get the equation, a plot of a phase diagram for a simple 2-component system, like kind of oil and water type thing. Like where is it going to phase separate? Because a delta G is a mixing. So if that goes positive, it demixes. That goes negative, it mixes. And so it's a combination of this enthalpic interactions that are kind of maybe driving mixing or not opposing mixing, and this entropic favors mixing. This favors mixing. This has a defavor. This thing's 1/T, so as the temperature drops, this becomes larger, and then it dominates over that, and then you get demixing, that low temperature. That's called a UCST because you have phase separation as you cool it. So the critical point is at the upper part of the 2-phase boundary. So it'd be like a UCST system, and just straightforward. All right, so there's that business. All right, so then there's, all right, so that's one way to write it, is just this Hildebrandt term. Another way to write it is say, I like this log format. I'm pretty comfortable with it. I can derive it 3 different ways. It's like, why not just stick with that format? And instead of log of x, log of something like x, something that's like a composition, but it incorporates this interaction thing. That's called an activity. So you have another way to write this equation in terms of activity. It's the same expression that you had for the ideal, except you put the activity in here to account for these interactions. Right, and then the activity is really proportional to the composition. So it's like the interactions plus the composition give you the activity, right? Times the comp. So in other words, you have the interactions, the deviation from ideal, and then the ideal. Multiply, give you this activity. So this thing's called the activity coefficient because it modifies the composition to give you the activity. So gamma times x gives you A. And if you plug in A, you get the free energy using the original equation. And then you have this gamma term, which reflects the non-ideality of the thing. Right. So if you have, say you have log of 100, so base 10 log of 100 is 2, and base 10 log of 10 is 1. So log of 100 is log of 10 plus log of 10. 1 plus 1 is 2. Right. So log of gamma x1 is the same as log of gamma plus log of x1. Right. So that means you can break this equation out. So this x1, x2, a12 equals this term, like this. So that's called the excess Gibbs free energy. You have the ideal plus the excess gives you the actual value. And the excess is going to be either x1, x1, x2, a12 is missing a 2 here, or this x1 ln gamma 1 gamma. So these activity coefficients become like a currency to talk about interactions. Talk about this Hildebrandt parameter. Right. So you have anyway, you have several different ways to kind of do this, right? They should all be related to each other, but it's not exactly clear. Like, how do you get a12 if you know gamma? That's kind of an issue, right? So because you have this log plus log gives you this just one number. It's like, how do you get that? So this is how you get that. So there's a way to get a12 from gamma. This is the way. So a12 times the other components composition squared gives you ln of gamma. And the same thing, so they mix and match like that. Right. So that thing comes from a little slightly messy operation, but basically, if you have the excess Gibbs, it's equal to this from the Hildebrandt. So this is a molar per mole. And if you want to know the actual value, you multiply that by the number of moles. So if you want to know the actual value, you put a bar under it. So that's the actual Gibbs free energy. This is a molar Gibbs free energy. So molar times number of moles gives you the actual. So you multiply by number of moles, the same thing. And then you realize that x1 is n1 by n, x2 is n2 by n. So then you have this n times the 2 term gives you a12 n2, and this is n1 by n. So you have this thing. And then if you take, so this is an expression in terms of a12. Then if you take the derivative of that with respect to n1, so that will, the derivative of the g of this, let's see, where's the thing with the gammas? All right, so this would have been GE bar would have been n1 times ln gamma 1 n2 ln gamma 2. So the derivative of GE1 with respect to n1 is just ln gamma 1 because of the, whatever that is. So x1 is n1 over n, right? So if you take the GE times n, then you end up with just n1 times ln gamma 1. Derivative of this with respect to n1 is just ln gamma 1. So that's where this thing comes from. And then you can take the derivative of this guy. So n2 doesn't depend on n1, so n2 just flops out there. And then n is n1 plus n2 and n1. So you can take the derivative with respect to n1 and get 1 over n. That's that thing. And you have 1 here. Take the derivative, hold n1 and take the derivative of n. And you end up with this 1 over n1 squared minus. So you get that term. And n1 over n is x1. And n2 over n is x2. And this is 1 minus x1, which is x2. So it gives you x2 squared times a12 gives you that thing. It's kind of a little involved, but basically you can relate the gamma to the Margulis thing, to the Hildebrandt coefficient or the chi parameter. Right? These things are the same thing. They're just related by the composition. As long as you just have one term here. This can get more complicated even in this, right? Because you have multiple terms. All these are going to give you a symmetric phase diagram. The gammas, the A's, the chi's, the whatever the other thing is, because it's just one term, so it has to be symmetric. So it has to be a symmetric phase diagram. So it's going to, let's see what it looks like. It's going to look like that. Like if you plot delta G of mixing over RT versus composition, it's going to be symmetric like that. And this is varying that term, that omega. Right. So when that thing is 0, that's called an athermal, like it has no temperature dependence. In other words, the free energy divided by temperature has no temperature dependence. So that's called an athermal mixture, the 0 term here. And then at some point, this expression, this omega matches that. So this thing's positive, that thing's negative, then your delta G is 0. When delta G is 0, that's the critical temperature. That's when this T goes to critical. When you have there's no free energy of mixing, it's just as happy mixed and unmixed. That's the critical phase separation point. So if you plot this out, now you're going up, 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 and then you reach like where this says 1, I guess it's flat, right? So at that point where it's flat, basically that's the critical point. And as you go up, this thing's going to end up having 2 minima in it. Well, you can't exactly see them, but there's 1 minima here, 1 minima there. Those are the two. So when the derivative of this with respect to composition is a chemical potential. So if you can draw a line across from that dip to that dip, those two chemical potentials are in equilibrium. So those are points of phases in equilibrium. And in the middle, the phase separates. On the outside, it's miscible. So as you go down, that dip point moves in until you reach a critical point, and then it should just come here. So your phase diagram will be like boom, 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 and then up. And then when this is negative, that's single phase. So it's just always like a smiley face. Right. So but if you go in with a composition of 0.2, so that's your mixture, and then there's a thermal fluctuation of composition. So you get part of it goes lower composition, part of it goes higher. Right. So the higher free energy is steeper than the one lower. That means that the sum of those two is going to give you an increase in the free energy, which is you want to decrease the free energy. So if you have a smiley face, it's going to want to stay where it is, because no matter where you are, the worst case is that if you're at 50%, then everything's up. So both sides lead to an increase in free energy. So you always go back to the thing. But anywhere on this concave up curve, you're always going to say if you add the two fluctuations together, that's worse off when it fluctuates than when it stays for the composition we put in. Right? The opposite is true of the frown face, the concave down. Right? Because in that case, everything, it stays where it wants, it stays wherever it can. The deviations persist. Right? It'll lower the free energy to deviate. So you can, anyway, we'll look at that again later on, but basically that's kind of how this thing works. So you can write that expression for the free energy, then you can make these plots as a function of temperature. You can find these minima, you can find the critical point. This is miscible, this is immiscible up here. As you cool it down, it becomes immiscible. It separates into those two compositions, one rich in B and one rich in A. And so that's how this free energy expression gives you the phase diagram of the thing. This is what I try to describe. Like you have 1 1s plus 2 2s divided by 2 subtracted from the 1 1 1 2s. Gives you the average energy, and that will give you this gamma number, the A12 number. Z is a number of, Z is a coordination number. It's like the number, like if it's on a lattice, how many interactions do you, in other words, if you're in a cubic lattice, there's 6 interactions with each site with the other guys. So Z would be like 6 if it's cubic. And Na takes care of something, moles versus number. Right, so anyway, so it's a little dry, but that's kind of how it is here. All right, so what is this thing? This is just showing that there's these excesses. So again, like this thing, if this was really following the Hildebrand, everything here would be symmetric. This isn't symmetric because let's see, this is SB, that's SN. I don't know what SB is. That's 10, right? Lead 10. That's like solder, and SB is something else. Anyway, so one has this is the change in volume on mixing. So one's a positive deviation, one's a negative. This is the excess, kind of the excess volume is the volume, because in an ideal system, there's no volume change, and there's no enthalpy change. But there is delta S, so you have a delta S mixing is going to be the ideal and then the non-ideal, and delta G is going to be the ideal and the non-ideal between these, right? So you can get this excess free energy, excess volume. If you have any volume change, it's excess. If there's any enthalpy change, it's excess beyond the ideal. Right, that's the ideal, the excess parameters. So let's see. Alright, so this is how this game is played here. So you have activity and you have a gamma, right? So because the activity, these are plots of the activity coefficient. So activity is gamma times x. Right. So if you do derivative activity versus x, in other words, if you plot activity versus x, the slope of that is gamma. Right, the activity coefficient. And then what you can see is that you're in nickel, and nickel is this curve. Right, so when you get to pure nickel, then the slope of this thing goes to 1, meaning that gamma is 1, meaning the activity is the same as the composition. So it's acting ideal when you get to pure nickel. Right, so that's called like Raoult's law. If these are gases, that's a Raoult's law behavior. When you get to high composition, it acts at the activity is just the composition, gamma's 1. And the same if this is nickel and iron alloy or something, then the same with when you get to pure iron, so 0 nickel, then that's also 1. Like in other words, a slope of 1 to 1 means that the slope is 1. Right. So in the pure components, you have gamma's 1 and it's acting like that's called Raoult's law. That's where you have ideal mixing behavior. There's no activity, it's just X. And then when you get to the dilute condition, there's another slope to this. There's a region at the low composition. You have another slope, and that's the infinite dilution gamma. That's called Henry's law. The dilute end doesn't behave ideally. That's the point. So when you dilute the iron down, so more nickel means dilute iron. The same with nickel. Dilute nickel has a gamma that isn't 1. And dilute iron has a gamma that isn't 1. So there's 2 slopes in this, 1 and then some other slope. Right. So this infinite dilution number is measuring kind of the deviation of the system from ideality. Like what's the interactions of iron and nickel in terms of from the perspective of iron and then from the perspective of nickel. Right, so if you have the Henry's law, this infinite dilution number is going to be useful if you have like a impurity, because down it's like 90% or higher. So if you have an impurity and you want to know like how it's mixing in, it's not going to follow Raoult's law, it's going to follow this infinite dilution law. Right. Whereas if let's say you have a solvent, it's going to behave Raoult's law. If you have a solvent, it's going to behave Raoult's law. If you have a solute, it's going to be Henry's law. Right, so you can. So anyway, that's kind of the point of this thing, I guess. We already kind of talked a little bit about Henry's law and Raoult's law, I guess, in general, but this is really the kind of like the basis of it, I guess. You can have all right, so this is from the book. All right, so you can talk about the chemical potential of a component and a mixture, right? So it's going to be the chemical component of if it's 2 phases, in phase whatever, right? So it's got to be the component and what phase it's in, right? So, and then also, in addition to that, so this chemical potential has a lot of defining terms involved in it. One is like, what is it of the material it is? And the other is what phases is it in? And the third is like, since you can't measure the Gibbs free energy alone, you need to have a reference point for it. So then you need to say like, what's the reference state that you're looking at? Is it in the 2 choices you have, or Raoult's law or Henry's law? Like you can say it's the major component. It's going to use a Raoult's law reference state for the chemical potential, or it's a dilute component, then use a Henry's law definition. And the reference point is going to be this business, like log of A1, which would be log of just X1, right? And then log of AH, which is going to be log of whatever that gamma from infinite dilution times whatever X you have. right? So AH is going to be gamma infinite dilution times whatever, and this is just going to be X. So just more complexity to these kind of chemical potentials that you get. Then, all right, so in the book, this is from the book. This kind of a mixture of the book and other things. So, like I mentioned, that you can have that this equation is a symmetric equation, right? So what do you do if it's not symmetric, which is most of the time, right? So I mean, you're gonna be dealing with some kind of polynomials of the Gibbs free energy, right? So it's gonna be either even powers or like some kind of mixture of powers like this, like x minus b to some power, and then xb is a prefactor. But so anyway, the way that works out in the end is the simplest one is the Margulis two parameter model, which is in here somewhere. Hildebrandt we already had. We got to talk about that, the del parameter here. Okay, so this is the two parameter model. So this, instead of having A12 times XAXB, you have A21 times XA, A12 times XB. This allows you to have asymmetry in the phase diagram. So the ideal is still symmetric, but the asymmetry comes from the interactions. So the interactions have this kind of skewed behavior. If you work through the same way, it's possible to get equations for how gamma 1 relates to the composition as A12, whatever. You can see it's going to be, this gamma 1 is going to be dependent on the composition of the, in other words, 1 and 2. So it's going to be skewed. In other words, they aren't going to be symmetric with each other because of the way these equations are written. And then if you know gamma and you want to get A12, you can also do that. So you can work these forward and backward. From gamma to A12, A21, or from A21, A12, there's gammas, two gammas. And that'll give you a smeared. This is a 2-parameter Margulis. You can have a 3-parameter Margulis. So you can go on to different kinds of skewedness of the phase diagrams. Right, but the ones that are, these are the main ones, like Margulis 1-parameter, Margulis 2-parameter. That mostly will take care of almost everything. Right, and then there's a lot of other. You can see this Redlich-Kister equation. It's got no limit to the number of parameters. Like he's got the original Margulis, and he's got A1, A2, A3, and then it's dot. So you can get like any number that he wants to add in. And you can convert this Redlich-Kister to the Margulis 2-parameter if you want. If you just take the first 2 terms in this, I think you can convert those two together. But okay, so there are a bunch of equations for this kind of thing. This is showing some data from propanol and water. Yeah.
Sorry, maybe I missed something basic, but when you say symmetric versus asymmetric, you just mean when you plot it, like you draw an axis of symmetry.
I mean, if you take 50% and then if you go left or right, it's the same thing. Yeah, so it's an axis of symmetry of 50%.
Okay.
Right, so I mean, you can see it here, right? So 1-parameter Margulis, they're trying to match up propanol and water. It doesn't match because it's skewed, right? So
Okay, yeah.
then 2-parameter Margulis, well, that's almost perfect. So, I mean, that's probably enough. You don't need to go more complicated than that. Just have 2 parameters, you can match up the skewedness of the thing. And then there's another Van Leer model, another model it has 2 parameters, I think. So, and there's any number of models for this you can use, but the Margulis is like the one that's kind of it's the simplest one. You know, that doesn't have any. I mean, you can. All right, so a lot of things can happen when you mix things. Like things can. So all of these assume that things are random. So Margulis 2-parameter says it just like maybe component A has a different affinity than component B has, so it shifts the curve over to the left, right? So, but you could also have like clustering, and the clustering can impact the other mixing things. There's a lot of different things that can happen. other words, you can have, this is assuming that the system is uniform. Both the Margulis 1 and 2 assuming the system's uniform. It doesn't have to be uniform. It could be like clustering. The clusters and these things don't work. Then you have to put in some kind of clustering model. And then there's also interpretation of those parameters. There's like an acid-base model to interpret the Margulis 2-parameter term, the 1-parameter term. You do, there's a variety of ways to interpret the terms. So that people make a living kind of just doing different phase models, you know. So let's see. All right, so let me go back here. I missed something. That business. So, hey, Dr. We can rip the A apart. And then over here, B, what does it take to rip B apart? Take the square root of that energy per volume and then subtract it and then square it. Average interaction energy. Kind of makes sense, I guess. No, but anyway, this is the formulation that people use, and it works. In other words, you can calculate the chi parameter that way. So you can get these cohesive energy densities in a table. Like you can look those up. And you can calculate these del's, or you can just get the del. And then if the del for two components is the same, then this chi is 0, and that means you have ideal mixing. In other words, it always mixes. So the difference between the del's, the smaller it is, the better off you are. The more likely the thing's going to mix. Right? It's kind of the difference between the del's normalized by the temperature. Right? And then you compare that with this mixing term, this ideal mixing term. And that will tell you if something's going to mix. So this makes it possible to say, like, I have this stuff and this other stuff. I can get these cohesive energy densities from the table, chemical table, somewhere, chemistry handbook or something. And then I can calculate the del's. And if the del's are the same, they mix. Like we were doing this the other day for oil and rubber. So you can calculate this cohesive energy density from a group contribution method. So you take oil has so many sulfurs in it and so many methyl groups and this and that, and you just sum those all up and you can calculate the cohesive energy density of oil. You can do the same thing for rubber. And then you can take the square root of that, get the del, and it turns out the del's are almost the same. That means that the rubber swells in the oil. But there's different kinds of oil, like aromatic and paraffinic oil. So you can calculate this del and just different kinds of rubber, like there's like SBR and butyl rubber and this and that. So you can figure out kind of what's going to mix with what. It turns out if this difference is less than think if this difference is less than 1 or something, or less than something like 1, whatever units, energy, square root energy units, joules or whatever, then this, the things will mix. If it's bigger than that, they kind of don't mix. Like there's a rule of thumb by the Stell thing. So you can also use it to directly calculate the Hildebrand mixing parameter and predict the phase diagram if you want. So people have turned that into like a pseudo science, right? So like this Hansen, so he's got different kinds of dells that have to do with hydrogen bonding, dells that have to do with polarization, dells that have to do with the dispersive. So however he wants to define those, basically you can add on other terms if you want. So you can talk about certain features of molecules or atoms and then get these Dell numbers and then add those up to get the final chi in this case, or the Hildebrand mixing parameter, or the Margulis parameter if you want. And then figure out what like polar things would mix with polar, things of hydrogen bond mix with things of hydrogen bond. Dispersive means, I don't know what it means exactly. Basically dispersive something to use in computer simulations. But so anyway, so this is a paper where they calculated these dells for carbon nanotubes. That's on the web page. Probably. This is lead. Oh, here, carbon nanotubes and polymers. So they but bigger. So that you can see they're calculating the del somehow here. Same thing that I just said, cohesive energy density, blah, 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 however they get it. They have the 3 terms. That's a standard like Hansen approach to it. And then they can calculate that for nanotubes and for whatever they're mixing it in. Different polymers. So you want to make a composite with a nanotube and a polymer. Which one's going to work? Like predict like which polymer would you use if you want to make a nanotube polymer composite. The problem is like these, the model assumes that everything is evenly dispersed in nanotubes. First off, you can have a single wall nanotube, but generally they're multi-wall, right? And the multi-wall and single wall don't behave the same way. They're not going to have the same del. Second of all, they don't. So things like this, because they have such high surface area, then they want it just like spaghetti, like line up together and clump up. And breaking apart that clump is going to be a whole separate operation. That's like a kinetic phenomenon. It's not thermodynamic. So it's basically getting that thing to actually disperse involves several deterrents, right? But you can't exactly get to the point where you have these things so uniformly dispersed that you can use a del parameter to describe the miscibility. What you can do is, though, you can predict, since you can't actually make the mixture that you want, you can say which one would be best and then stick with that system and then try to mix it, try to get it to mix. Right. So this is more like a tool, a predictive tool to understand like which system do you want to work with. This is a papers about simulations, but basically it's along the same lines, right? Just I don't know. These are what are these? Just the plots of del versus. Oh, they're treating the nanotubes to get them to mix. They can calculate how the del changes as they treat the surface. You can see it's kind of all the same game. Like here's the delta H with the chi parameter. There's the del squared thing. You know what R is? R must be the size, I guess, but I don't remember. Right. So anyway, you can see like, hopefully you can see that there's like the same stuff that's just being kind of repeated, you know. If you see a few papers, you can kind of get a feel for where things are going here. Asymmetric, I mentioned that through this. So you can see like the gamma, so when you go to dilute, when you go to concentrated, so x1, gamma 1 goes to 1. That's 1 here. When you go to concentrated 2, gamma 2 goes to 1. So that's a Raoult limit. And then when you go to dilute of 1, gamma 1 goes to some value, that's the infinite dilution number. And then gamma 2 goes to some value when it gets dilute. That's the infinite dilution number. Right, so you can kind of see how this pans out. Like this is a plot of the phase diagram, I guess here. Well, no, it's a vapor pressure. Let's see, what is this plot of? A data points. I don't know what that's exactly. I think it's a vapor pressure, but pressure. Yeah, this is a separate thing. We don't want to look at that exactly. All right, so yeah, we got a couple of minutes. So the other thing is that if you want, so you have this 1 over t dependence, right, of this. So gamma omega should be 1 over t. So what do you do if you, so the systems where the thing can phase separate on heating. In fact, in polymers, that's like the normal way. So if the polymers, all right, so all right, so we had this this phase diagram. So if you plotted delta G over KT versus composition, you're going to get this thing where that's low T and then high T. This thing's going to go like this. We have these two minima, and the slope of that is the chemical potential in phase A and phase B. Chemical potentials equal each other. So if you plotted this out, so this is x1, then you could have points there, and at some point this would go flat, so that's your critical point. So you'd have those points, and then you'd have this. Let's see, I got that upside down. Anyway, if it's a UCST, this phase diagram will look like that. Then we have the critical point here. That's a critical composition, and this is a critical temperature. So it's temperature versus composition. This is 2 phase. This is 1 phase. That's called a UCST, upper critical solution temperature, because that's at the top. And in that case, you have the omega, or the A12 is going to be the average delta E, Z, and then KT or RT, depending on how you want to do it. Right, so it's got this 1 over T, so that when the temperature gets high, this positive term gets small, and then you just have the negative term ln x plus x ln x. That term dominates because this term gets small. The A2 plus x ln x2 A12. So if this thing gets small, this is negative, this is positive. So as the temperature goes up, then the positive thing goes away and it mixes. So it mixes into 1 phase at high temperature. At low temperature, it goes 2 phase. That's the 2 phase region, right? So if instead of having 1 over T, you have like A12 is some constant. So call it just K, then plus, so call it A, and then just call it B over T. Right. So in that case, you can make it mix when it gets to high temperature. So B is a negative number. Right. And then also, if it's a polymer, this is divided by N. So that goes to 0 basically. So it means, because if N is 100,000, then there's like no entropy of mixing. There's no like random, because they're just like a few polymers in there. There's not enough entropy for it to change to drive the mixing. Right? So in that case, you need to have a negative B term to make it mix. It won't mix unless you have that. So you could have that if there's like a polar interaction between the polymer and the solvent or something, or polymer and another polymer. They have some kind of ionic interaction that drives them to mix. Right, so you have a negative enthalpy. There's a drop, the enthalpy drives the mixing, drops the free energy. It's going to be delta G over KT. Right, so anyway, so if you have a negative over temperature, and then this thing's positive, so this thing demixes, that mixes, as the temperature goes up, it demixes, because this negative term drops out. And then in that case, you can get a, let's call it LCST, lower critical solution temperature. It looks just like the upper critical, but it's upside down. Right. So that's kind of what this is getting at here in kind of a difficult way. It's trying to say, like, well, you can have this thing split into two terms. One's temperature dependent and one isn't. Tau I think is T minus TC over T. So it's a little complicated here, but anyway, this is going to be 1 over T, right? So it's written kind of funny. The A plus B over T thing is easier to understand. Right, basically, you're going to have two terms. One's temperature dependent, one isn't. And that will give you this ability to have a phase separation on heating. So it's a weird thing. Like if you have some polymer like Post-it glue, sticky. If you try to wipe it up with hot water, it doesn't wipe up. But if you wipe it up with cold water, it just wipes up. So it's kind of the opposite of what you think. Cold stuff dissolves it. So anyway, there's a few polymers. I mean, all polymers basically mix that way because there's no entropy of mixing. The only way they would mix if you had an enthalpic interaction that made them mix. Almost all polymer mixtures are going to be like that. And some other systems have that same behavior, like biological systems have that kind of behavior. Like they wouldn't normally mix, they only mix because of an enthalpic interaction. So you can see there's a lot of twists to this simple model. Like the model is just like you add an AB interaction, some term that's going to be symmetric, so make it asymmetric. That's going to always phase separate on cooling. So you fiddle with the numbers to make it phase separate on heating, and various other things you can mess around with it. But the model, so if you see it, there's any number of things that people can do with the papers on this, right? But basically the thing you have to know is that the epsilon x, epsilon x, like you should feel really comfortable when you see that. That's ideal mixing. It's like you'll see some long equation, blah, 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 then it's epsilon x, epsilon x. I know that part. And then the other part is going to be the enthalpic part. And that could be like A times B, or it could be some other more complicated thing, right? So that's going to be explaining like what's actually going on. Like there's always going to be this ideal mixing term. This part is a part that will like become involved, become more complex, and you can mess with that any way that you want to, as long as it makes a little bit of sense. But anyway, why don't we quit there? So it's coherent enough for today. Any questions or anything? No? Hey.
That's what I thought.
Yeah. All right.